Chapter 8, number 27. A 0.26 kilogram rock is thrown vertically upward from the top of a cliff that is 32 meters high. When it hits the ground at the base of the cliff, the rock has a speed of 29 meters per second. Assuming that air resistance can be ignored, find the initial speed of the rock and the greatest height of the rock as measured from the base of the cliff. So, here we're going to do this almost certainly as an energy conservation. So we have our cliff, and we are given that the height of the cliff, that's a known number, which is 32. And we start off with the rock being thrown vertically upward. I'm going to give it as if it had a little motion over width, but it doesn't actually have to be. It could be like held over the edge and thrown up and come straight down, so we don't have to worry about sideways motion. But it does something like this, and it falls here. And I'm going to call the greatest height that it has, capital H, the initial velocity, which is what we're looking for, I'm going to call V0. The final velocity, I'm going to call VF, right before it hits the ground. And we know some of these things. For instance, we know that VF is 29 meters per second. And we know that H, little h, is 32 meters. And what we're looking for is big H, and we're looking for V0. All right, so our first thing we can do is we can say that the energy at the start, which I'm going to call here, is equal to the energy at the end because air resistance can be ignored. So we have only conservative forces acting once it leaves my hand, or whoever's hand. So we can say something like the energy at the start is the energy at the end. That's the kinetic energy at the start plus the potential energy at the start is the kinetic energy at the end plus the potential energy at the end. To go any further, I need to have a reference frame. I'm going to choose the ground to be y equals 0. Because of that, then I can say that at the end I have no potential energy. All right, I only know that because I'm saying that. I'm defining it to be true there. I could pick other places, but in general, the lowermost leftmost point is your most convenient one. So we have something like 1/2 mv0 squared, that's the initial kinetic energy, plus mg times the initial position, which is h, is equal to 1/2 mvf squared plus mg times 0. That's why that ends up being 0. And then we just solve this for v0. So we bring the mgh to the other side, and we have 1/2 mv0 squared equals 1/2 mvf squared minus mgh. And then we multiply by 2 over m so as to clear out that and have v0 square. But to do that, we have to then multiply the whole other side by 2 over m, and that gives us vf squared minus 2gh. So v0 is square root of 29 meters per second quantity squared minus 2 times 9.81 meters per second square times 32 meters. You might notice the mass has dropped out. That is not uncommon when we're talking about just gravity. Since gravity scales with the mass, it often just drops out of everything. You should always keep it at the start, though, because there'll be problems where it doesn't go away. But when it does go away, you should feel comforted. You're like, okay, I expect that. V0 ends up being 14.6 meters, or really 15 meters, because we only have 2 sig figs, which is fine. All right, that was part A. To do part B, we're going to do something very similar. And the way I'm going to choose to do it is I'm going to say, let's create some other moment that we care about, which I'm going to call moment 1, where the ball is at the highest point. And I'm going to call that time 1. And so energy is still conserved, so I can pick either of the other energies and make them equal to the energy at the highest point. And I'm going to choose to take the final energy, It really doesn't matter, but I'm going to choose to do that one. And so I'll have K1 plus UG1 is KF plus UGF. But we know a couple things. We chose our reference frame already that this is 0, so I'm going to get rid of it. And being at the highest point means the velocity is 0, and therefore so is the kinetic energy. And we end up with a more interesting thing that says that the final potential energy, or the potential energy at the top, is equal to the kinetic energy right before it hits. This is reference frame dependent, but we set it up to make that happen. So we have mg capital H is equal to 1/2 mvf squared. And now I can cancel the m's again. That's kind of interesting. As said before, often in gravity, things like that cancel, and I'm left with vf squared. Oh, let's do it differently, sorry. I'm left with gh equals vf squared over 2. So big H is vf squared over 2g. So it's 29 meters per second quantity squared over 2 times 9.81 meters per second square, or 42.86 meters, which is really 43 meters. Also, just notice back here, the wrong units down here. These are meters per second because clearly velocities. And that's why you should really track it as you go through, but it worked out anyway.